And continuing on the back of the regular physics review guide for the forces, friction, snow tubing test, number 10, a 15 kilogram book is pushed with a force of 460 newtons across a table at constant speed. Free body diagram of the book. Remember to always draw your free body diagram. You'd have the applied force, you'd have the force friction, you'd have gravity pushing it into the table, and you'd have the normal force of the table pushing up on the book. Kind of see that? What is the coefficient of friction in the book? These are balanced in both directions. So the force pull is equal to the force friction, which would equal 45.6 newtons. And the force normal is equal to the force gravity, which we've only got a mass. So I'm going to have to take 15 kilograms times 9.8 to get the force of gravity. Then we can relate it to find mu using force friction equals mu times force normal, where you plug this in for the normal, you plug this in for the force friction, and you can solve for mu. If the book is then pushed with 60 newtons, so you're applying a greater applied force than the friction is, so now you will begin to accelerate. So we're doing F net equals ma, and remember this is the helping force minus the hurting force equals the mass times acceleration. So 60 newtons minus the force of friction, which is 45.6 newtons, and that would equal the mass, which is in kilograms, so that's just the 15 kilograms times A. And now you could find the acceleration. The only difference in the free body diagram is that the pull now is a longer arrow than the friction, but gravity and normal force are still balanced. So that's what the one difference would look like in your picture. If two books are pushed across the table instead of just one with the same 60 Newton force, what would be the result? So if you just put two books, that would mean that you've increased the force of friction and you've increased the mass. So it would be less acceleration, and I think they just wanted a conceptual answer on that because you've got more hurting force and you've got more mass, so you're going to have less acceleration. Then the snow tubing problems. A new skier tries out the bunny hill. He uses a tow rope to get pulled up the 8-meter hill. He's got a mass of 45. How much work does it do? Work is the force times distance. So the force on him would be 45 kilograms times 9.8, and it's moved up a vertical distance of 8 meters. If it takes them 2 minutes 45 seconds to get to the top, what's the power? Power is the work per time. So you take whatever you got for work from above, divided by the time. 2 minutes is like 120 seconds plus another 45 would be divided by 165 seconds to get power. Remember, power is in units of watts. In number 12 then, if the skier from problem 11 is now at the top of the hill ready to slide down, how much potential do they have? Potential equals mgh. So that would be 45 times 9.8 times 8 meters, which notice that's equal to the work because you put in work to now give yourself potential energy. And this will have units of joules. Sorry, that was joules. This would also be in units of joules. How much KE should he have at the bottom? That's the idea that the potential energy the skier has at the top should equal the kinetic energy they have at the bottom. And when he gets to the bottom, his friends find that it takes him 1.76 seconds to go 10 meters. So you can solve for like the experimental velocity using v equals d over t. So I'd take 10 meters divided by 1.76 seconds. That would tell you how fast he's really going. And to figure out how much kinetic energy he really has, use Ke equals 1/2 mv squared. So 1/2 times 45 kilograms times this velocity that you've calculated squared. Why might they end up being a little bit different? Remember, one is theoretical, and theoretical value does not consider friction. It's assuming it's perfectly frictionless, where in the real world that's not going to be always the case. And then for number 13, a 55 kilogram sledder sleds down the hill with a coefficient of friction of 0.231. At the bottom of the hill, the sledder coasts to a stop. What's their deceleration? So F net equals MA. And the net force on them is going to be negative of that force friction, because that's what's going to be stopping them, because you'd have force friction, force gravity, force normal. Notice vertically it's balanced, so the gravity and normal force will equal to each other. So negative mu times mg equals ma, and you notice a cancels. And this is where we got the equation that negative mu 0.231 times g, 9.8, equals the acceleration. And it's a negative acceleration because he's slowing down. And then if you reach a speed of 6.4 meters per second at the bottom, how far would he coast? We can go back to the old motion equation. Vf squared equals vi squared plus 2ad. Final velocity would be 0. Initial velocity would be 6.4 squared plus 2 times a, whatever we got up here, times d, and you can solve for the displacement. And that's all. Thank you, and happy studying.